All right, so today I am covering nth roots, and I'm going to be going over just the basics here. I'm not going to go into all of the details of nth roots because it's not really what we're focusing on in this class. You just kind of want to know the basics. It's going to be covered in much more detail in college algebra. So first, I just want to start off with a table of perfect powers. So we talk about perfect squares, which are numbers that are squares of another number. And so there are also perfect cubes, perfect fourth powers, fifth powers, basically any exponent. And so this table is the ones that you should have memorized, or especially perfect squares up through 13. I also have 15 squared memorized. I don't have 14 squared memorized for whatever reason. Perfect cubes, you pretty much only really know up to 5. Powers of 10 you should know. Those are pretty easy. The fourth power is probably up to 3, and the fifth you only really need 1 to the fifth and 2 to the fifth. So we are going to be using these. You want to have this as a reference. You should try to memorize these because it will make your life easier, especially if you have to go on and take more math classes. So before we get into nth roots, we're just going to focus on recognizing when things are perfect squares, because when you're taking a root, you're undoing exponents. And so we need to be able to recognize the types of exponents that we have so that we can undo the process. So the key here is that perfect squares can be written with an exponent of 2. So if I go back, all the perfect squares were things that were squared. So written with an exponent of 2. And sometimes you have to do a little bit of manipulation to put it in that form using our rules of exponents that we learned about in week 4, when we're learning about the properties of exponents, like the power of the power, multiplying exponents together, all of that kind of stuff. So we're going to be using those rules, but basically in reverse to kind of rewrite these. So it's a perfect square if we can write it so that it has an exponent of 2. So the first one here, top left, is x squared. That has an exponent of 2. So that is a perfect square. That one's easy enough. Second one, we have a cubed. So our rules of exponents are, we can either write it as when you combine exponents, you add them. So we could try to rewrite it to the exponent of 3 here so that it's like maybe 1 plus 2 or 2 plus 1. And if we do that, like say a to the 1 and a squared, one of our exponents is an exponent of 2, but the other one isn't. So it's still not a perfect square because one of the exponents isn't something of 2. So we don't really want to use that rule. What we want to do is use the rule where you're multiplying exponents and see if you can try to rewrite that. So you would say, okay, what 2 numbers multiply to 3, and is there a way I can make 2 one of those? And in this case, there isn't a way to do that. Like if you tried a to the first and then to the 3, that gives you a cubed, but it still don't have an exponent of 2. So if you can't make something have an exponent of 2, it is not a perfect square. So let's look at y to the 4th. So it does not have an exponent of 2, but can we rewrite it so that it does have an exponent of 2? So one way we can do this is to split up y to the 4th as y squared times y squared. So both of those have exponents of 2, so those are perfect squares. And that's one way we can do it. The other way is to recognize that y to the 4th is y squared squared. Because you see when I split it up above, there was 2 y squareds. So that's basically taking that exponent rule where you multiply the exponents, and we're kind of dividing it by 2, and 4 divided by 2 is 2, so there's 2 left over. So either way here, we have rewritten it so that our variables have exponents of 2, which makes them perfect squares. So y to the 4th is a perfect square. So now we're going to move to z to the 5th and see, can we write this in such a way that everything is, has an exponent of 2? So the first is to try to do what we did with a cubed. You try to split it up so that you can have something with an exponent of 2. So like if we have z to the 5th, that means we have 5 z's. So we can maybe have 2 z's, another 2 z's, and then we have 1 left over. So we could try z to the 5th as z squared, and then we have 1 more z left over. So we still have 5 of them there. So 2 of those are perfect squares, but the z to the 1, that's a problem. That's not a perfect square. So then you say, okay, can I try to rewrite it so that it's, I try to use the product rule with my exponents where I multiply them. Can I take my exponent divided by 2 so that they're 2 things multiplied together? And one of those numbers is 2. And 5 doesn't divide by 2. So we can't rewrite this so that everything has a power of 2, or you can divide the exponent by 2. So it's not a perfect square. So let's look at AB to the 6th. So same sort of thing. We want to either see if we can rewrite it using our rule of adding exponents where everything is a power of 2, so that they're perfect squares, or where we can rewrite it so that way if you divide the exponent, or you multiply the exponent to one of those exponents is 2. So there's 2 ways to do this. If we try to rewrite it, we can group them. So AB to the 6th means there's 6 of them. So we can group them in pairs and have 3 pairs. Oops, I wrote 3 there. That's a 2. So all of those have exponents of 2. So that means that this is a perfect square. Another way we can write it is to recognize that if we divide the exponent by 2, we get 3. And so you can think of it as you have AB cubed twice squared. Or we could do it the other way around. Say we have AB squared 3 times. But either way, there is an exponent of 2. And that exponent of 2 means that it is a perfect square. So you may be noticing a pattern here with perfect squares that are even exponents are perfect squares, odd exponents are not. And that is a true statement when you're looking at these things. So even exponents are perfect squares. Odd exponents are not. So using that rule, if we see PQ to the 7th, this is not a perfect square. We can try to split it up in groups of 2, but we're going to have 1 left over because we'll have the same number that we did for 6, but then there's an extra grouping here that doesn't have an exponent of 2. W to the 8th is a perfect square. CD to the 9th, not a perfect square. And M to the 10th is a perfect square. So let's go back to my list where I had these perfect squares, perfect cubes, perfect 4th powers. Notice that all of the even exponents here, the ones that are under the 4th power, are also on our perfect square list. So anything with this even exponent is also a perfect square. The cubes don't come out that way. You can see the numbers, only one of the numbers that's a perfect cube is on the perfect square list, and that's 4 cubed, and that's special because 4 is 2 squared. 2 to the 5th, that doesn't, that doesn't show up. The ones are special as well. So any even power is a perfect square, and that's important when you're looking at taking square roots. So nth roots, n means any number. So you can have 2, which would be a square. You can have a 3, which is the cube, 4, which is a 4th root. So you need to be able to recognize what type of perfect thing they are. And so for perfect squares, it has an even exponent. So that's really important. So now let's look at perfect cubes. So the idea here with a perfect cube is that you want to rewrite it so that it has an exponent of 3. That's what it means to be cubed, exponent of 3. So x squared doesn't have an exponent of 3. We can't make 2x's suddenly have 3x's. So that is not a perfect cube. A cubed, that has an exponent of 3, that is a perfect cube. Y to the 4th. So we want to try to group these things so they have exponents of 3. So y to the 4th, we could try a y3, but then we need to have one more y to make up to 4. So that would be a y first. Now to be a perfect cube, that is a really terrible one. All of the exponents need to be 3. So the y1 causes a problem. It's not an exponent of 3, so it's not a perfect cube. Z to the 5th. So we want to try to get exponents of 3. That's what it means to be a perfect cube. So I could rewrite z to the 5th as z to the 3, but then I need 5 of them, so I need 2 more. So one of those is a perfect cube, z cubed, but we have z squared. That's not an exponent of 3. So that is not a perfect cube. A to the 6th. So we want to rewrite it so it has exponents of 3. We've got exponent of 6. So this means there's 6 of them, but we can group them in groups of 3. So we could have AB cubed and then another AB cubed. So we can split that 6 up to 2 groups of 3, and those are perfect cubes because they have an exponent of 3. So a to the 6th is a perfect cube. So just to compare, notice that a to the 6th was also a perfect square. So you can have some overlap there, but not every number overlaps. Not every perfect cube is a perfect square. We talked about that when I had this list here. 4 to the 3rd equals 64. That is a perfect cube and a perfect square, but not every cube is a square. So notice that while we were looking for perfect squares, it seemed to be like every other exponent was a perfect square. For cubes, it's not every other, it's every third. Basically, any exponent you can divide by 3 is a perfect cube. So I want you to notice this pattern of dividing the exponent. So perfect squares, they were even. You can divide the exponent by 2. Perfect cubes, you divide the exponent by 3. So perfect cubes have exponents divisible by 3. So p to the 7th, 7 cannot be divided by 3, so it is not a perfect cube. W at 8, 8 does not divide by 3, so that's not a perfect cube. CD to the 9th, 9 can be divided by 3, so this is a perfect cube. And then m to the 10, 10 does not divide by 3, so it's not a perfect cube. There's a lot fewer perfect cubes than perfect squares. So this idea that your exponent needs to be divisible by this number, that's really important for nth roots. So that's where we're going next. So we need to talk about this symbol here, the radical symbol. Or also it's called the radical symbol. We use this to find roots. So that's the symbol we use to find the square root. So the word radical and root are kind of interchangeable here. Radical. I think of them kind of as the same thing. So we use this symbol for square roots specifically, which is where we're kind of undoing an exponent of 2 or a perfect square. So all of those perfect squares you can take square roots of, and that's something we looked at week 1. So when you have this radical symbol, everything that is under that top line, so everything directly under it in this little shaded area, is inside or under the radical symbol and part of the root. If you have anything that's outside of that, it's not part of the symbol. So this is one of those things where you really need to pay attention to the little details, because where the line stops matters. So if I had the root stop at 5, then +2, that is different from 5 + 2 with the line going over it. Those are not the same thing. So it's really important to know that difference. Now we have variations on this symbol where we add a little number in the upper left. So an example would be something like this. So I might have a 5 kind of in the upper left above the little V thing. That's a root, an nth root, in this case, a 5th root, because it's a 5. So that's where we're going when we talk about these nth roots, is we're looking at more than just square roots. So square roots undo things that are squared. We're looking at undoing things that are cubed, undoing things that have a 4 further exponents. So we're looking at undoing other exponents. And so we just refer to these as nth roots, wherever that n is just that number that you see kind of above the symbol. So going back to basics, back to the square root, which you guys know, b, some number is a square root of a if when that b is squared, it gives you the other number. That's what it means to be a square root. The definition is in terms of the exponent, not the actual symbol we use to indicate taking the square root. So the definition is based off of what it means in exponents, but we use this symbol for the radical as the action to do the reverse, basically, to undo what we have going on. So 3 squared is 9. So that 3 is a square root of 9, because if you do the square root of 9, that gives you 3. Basically, that action of square root of 9 says, what number squared gives me 9? And that would be 3. Now, this -3, when you square it, also gives you 9. You square a negative, you get a positive. So when you say, let's find the square root of 9, your answer could also be -3. So there are actually 2 answers when you take square roots, because there are 2 ways to square and get a number of 9, one with a +3 and one with a -3. So we usually work with the positive. That's what your calculator gives you. And that's what's called the principal square root, where we just use the positive number. Your calculator, if you did square root of 9, only gives you 3. It doesn't give you -3. And that's good enough for most of the time, except for when we start solving. So when we start doing things like the quadratic formula, which we will be, you'll be looking at this week, is the quadratic formula. When you start solving, you want both answers. So we use a special symbol that we put in front of the radical symbol that's called a plus or minus. So it's a plus and then a minus underneath it. And that means we want both the positive and the negative. So you have to remember that there's two answers, a positive and a negative possibility here with the square root. And so when you do it on your calculator, it only gives you one. You have to know to add in the negative because your calculator is not going to tell you that. So that's one of these things where you can't always rely on a calculator because it will only give you one of the answers here. So that's the square root. And we're going to be looking at nth roots here just to kind of go beyond and to look at these other things. So an nth root is looking for what number, when I take it to this exponent, gives me this other number. And just the exponent is not 2. Could be 3, 4, whatever. It's still undoing exponents. It's just undoing other exponents. And so we have our radical symbol, but we have a little number kind of above that V. We call that number the index. And then the number underneath or inside your radical is called the radicand. Very, you're probably like, oh man, all this, the vocabulary, a lot of vocabulary, but it's not so bad. It's not so bad. It's just kind of introducing you to a new type more than just a square root here, but it's kind of the same idea. So you may be wondering, well, why does the square root not have a number, but other ones have a number? You can write a 2 up there to indicate a square root. It's just we usually don't because we do square root so often. It's just assumed that the radical by itself means square root. So we just always assume it's a square root unless there's a number there. So the 3 gives us a cubed root, and that will undo any exponents that are 3. So the cubed root of 8 gives us 2 because 2 cubed is 8. So you're asking yourself, if you have 8 and you're trying to find the cubed root, you say, what number cubed gives me 8? You're looking for, so let's say if I have a cubed root of 64, you're saying, okay, you're asking yourself, what number cubed gives me 64? That's how you're thinking about these in your head. And that's why you need to know your perfect cubes. Because in order to find a cubed root, you need to know your cubes, because that's how we define it. We don't memorize cubed roots, we memorize the exponents. So you go back to your chart here, and you're looking at your perfect cubes, and you look for the cube that looks equals 64, which is 4. 4 cubed gives us 64. So our missing number here is 4. So 4 is the cube root of 64. That is the missing number there. That cubed gives us 64. So that's why I spent that time in the beginning here with these perfect squares and perfect cubes. First, perfect cubes, because those are the second most common that we see. But because you have to be able to recognize it's one of those in order to go backwards and take the root. So with cubed roots, you can have negatives inside there because a -8 is -2 cubed. So our table only has the positive numbers for the exponents, that table that I showed, but you can have negatives as well with that exponent. So you just have to know that, when you have an odd power on a negative, your output is negative. Even power on a negative, your output is positive. So that's the idea of the nth root, is we're undoing other exponents. And so you have to kind of know how you can rewrite it as that exponent in order to find the answer. So when you're taking roots and you have things with exponents, basically this root, this radical is canceling out the exponent. They're undoing each other, but we do have slightly different rules depending on if the index is odd or even. So for odds, they just cancel out. Whatever number is underneath it is the number. So an example of this, if I take a cubed root of -2 cubed, I get -2. And if I take a cubed root of 2 cubed, it gives me 2. It just cancels out that exponent. For even integers in that index, like a square root, it's different. So I'll use a square root as an example. The square root of -2 squared is actually going to be +2. You take the absolute value. So you take the absolute value of whatever was underneath the radical. Because of the definition, you can't have, if I said that this was -2, then I'm asking -2 squared. I'm saying what squared gives me, what squared gives me basically this -2 squared, which is equal to 4. And if we were saying the answer is -2, well, there's really 2 answers here. 2 also gives you 4. And it's kind of like, well, how do we know which one you want? So we just always give the positive one. So we have to have positive answers. As our, if we're taking a even root when you have something with a negative there. So we're just always going to use the positive. So if it's a negative in there, you have to take the absolute value first. So if it's already positive, it doesn't matter. We're just trying to be consistent here because of the fact that there's more than one way to get numbers, and you want to be very clear. In the odd, there's only one possibility to get, like -2 cubed is -8. There's only one way you can get there. 2 cubed equals 8. There's only one way you can get there with odd numbers. But if you're saying 4, that could be -2 squared or 2 squared. So we make this decision that we're always going to use the positive there. So we take the absolute value. We're just saying we can't have those negatives there. You're never going to have a negative output of a square root. So that's sort of just to keep things consistent. And once you get into college algebra, you'll start seeing more detail why this is the case. So that's how it kind of works with numbers, just to make sure there's consistency. And if there's variables, because we don't know if the variable is a positive or a negative number underneath there, we just always assume we're going to get a positive, and you don't have to worry with the absolute value part. We just are going to make an assumption that whatever is the variable, it's going to be a positive number. So you only really have to worry about these absolute values when you're having actual numbers, and only when it's in this form. So now that we've kind of discussed that, we are going to simplify these nth roots, and we're going to just practice what we just saw, basically. The fact that the nth root will cancel out the n exponent. So we've got cubed root of 3 to the third. The cube in the index cancels out the cube in the exponent, and all we're left with is 3. So you're only left with whatever is kind of underneath your exponent here. That's our answer, because the root and the radical, or the root and the exponent cancel out. So moving over, that means that our answer to the cubed root of -3 cubed is going to be -3. Again, those are going to be canceled. You're just left with whatever is inside. So that's going to be -3. Now, here on the right, we've got a negative on the outside. So that is separate from the radical. So you take care of the radical first, and then you have this negative. So you can think of this as having a negative and then parentheses. It's like a -1. Let's do that. So it's a -1 times your radical there. So the cube root cancels out the cubed exponent, which leaves us 3. So we have -1 times 3. And so your answer here is a -3. So you have two ways to get -3 here. If the negative is in the inside and it's inside the parentheses, or if it's on the outside there. So let's look at our second row. Now we've got 4th roots. So we're undoing exponents of 4. So 4th root of 4 to the 4. I have lots of 4s here. The 4th root cancels out the 4, the exponent. So we are just left with the 4 that's underneath. So that's going to give us 4. Next one here. This is a situation where we have to use the absolute value because we have an even exponent. So it's the absolute value. I didn't do the absolute value with the 4 because that's already positive, but we have a -4 here. So this would cancel out to give us -4, but we have to do the absolute value. It's the absolute value of -4 that this cancels out. So our answer is actually 4. And then on the right here, this is again, it's like a -1 times whatever your radical is here, 4th root of 4 to the 4th. So that would be -1 times 4. So you get a -4 here. So for even exponents, the only way you're getting a negative out when you take the root, or for even roots, is if the negative is outside of the radical symbol. So these are important kind of little things to know. Bottom, I have other exponents here. So we've got the 5th root. Even if you've got a fraction inside here, the 5th root will undo the 5th exponent, and you are just left with 1/2. Here I've got 1, and we've got a -6th root of 1 to the 6th. So that 6th root cancels out. The exponent is 6, which leaves us just a 1, and then we have this negative. So we're going to get -1 here. And then we've got 0. So 7th root of 0 to the 7th. So again, the 7th root and the 7, those cancel, and we're just left with 0 as our answer. So simplifying nth roots, not too bad. We're just looking at undoing these exponents, and basically that's what it does. What the nth root does is it undoes this matching exponent. And the only tricky thing is if you've got a negative, you would have gotten a negative, but it's got an even index, or it's an even numbered nth root, then you have to do this absolute value thing. So we can apply this to variables as well. So with variables, we don't, it's actually kind of easier. So with these numbers here, we're just strictly using the rule where it cancels things out. Now, I just want to go back to at the very beginning when we were talking about these things here, perfect squares, perfect cubes. So we made this observation that things were perfect squares if they had even exponents, or we could divide the exponent by 2. And things were perfect cubes if you could divide the exponent by 3. So this idea of being able to divide the exponent by whatever if you're looking for cubes, it's 3, squares 2. That's kind of the index. We're dividing the exponent by the index. And so that is the idea between finding nth roots when we have variables. And you could use it with numbers as well, but normally we use it more with variables. With numbers, we kind of just use our calculator to get the numbers. So what this means is for square roots, to take the square root of something with a variable, you have to be able to divide the variable by 2. So the square root of x to the fourth is x squared. 4 divided by 2 gives you 2. The square root of x to the sixth is x cubed because 6 divided by 2 is 3. So this is, oops, let me not be in yellow. So if I take the x to the sixth, we can make that a perfect square by writing it as x cubed squared times x cubed squared. That's one way that we could do that, is rewrite it so that it has exponents of 2, and then you can see they would cancel out where we've got x cubed kind of there underneath it if we rewrite it. Oops, that's too many of those. I only need one of these. There's x cubed 2 squared, so we can rewrite it there. And so when the square root will cancel out the square and you're left with x cubed. So that's where the dividing by 2 kind of comes from. The other way we were looking at it, I was trying to do both of these at the same time because I was having a brain fart, would be x squared times x squared times x squared. Well, when you take the square root of both of those, all of the squares cancel. We're left with x times x times x, which is x cubed. So that's sort of the idea behind being able to cancel out and just divide your exponent by 2. So for cubed roots, that means you're dividing by 3. So x to the sixth, you divide by 3, that gives you x squared. X to the ninth, you can divide 9 by 3, that gives you x cubed. So you want to be able to take your exponent, divide it by the index. If you can't do that, you can't take the root without some tricks that you'll learn in college algebra that we're not focusing on here. So this works with our letters, but we're going to just apply it to variables here. And again, we're going to assume all these variables are positive, so you don't have to worry about absolute value stuff. So first few are just strictly using what we did for numbers on variables. So the fourth root of k cubed to the fourth root and the 4 cancel, which leaves us, oh, I don't want to be in red. Make that back yellow. It gives us k cubed. wy squared, so the square root cancels out that square and you're just left with what is underneath it, which is wy. Let me just kind of highlight these. And then cubed root, that's one, you don't worry about the absolute value of cubed roots. We have a negative k cubed inside the cube root. The cubed root and the cube cancel, you're left with negative k. So that's basically the same thing that we did with the numbers, where you just, it just directly kind of cancels out and you're left with whatever was underneath it. The next ones, we're going to use this trick of dividing the exponents. So I have the fourth root of s to the 60. So to simplify this, to take the nth root, you have to be able to divide that exponent by 4. So 60 divided by 4 is 15. So our answer here is s to the 15. So what happens if we have a cubed root instead? You're dividing by 3 instead. It's going to be a different answer. So 60 divided by 3 is 20. So this one comes out to s to the 20. So what type of root it is matters because you get a different answer when you try to simplify it. Next, we have the square root. So that means you're dividing it by 2. So 60 divided by 2 is 30. So this is going to give you s to the 30. That looks like a 5. Really there. I don't know if that's any better. Oh, whatever. It's an S. It's a terrible looking S. And let's look at the bottom here. So I've got the cubed root of x to the 33. So cubed root, divide that exponent by 3. 33 divided by 3 is 11. So you're going to get out x to the 11th. Then we have the cubed root of x to the 27th. 27 divided by 3 is 9. So your answer is x to the 9. And then we have the fifth root of z to the 20. So 20 divided by 5 is 4. So you get z to the 4. So simplifying here, when it says simplify, let me grab a different color here, means to take the nth root. Your goal is to get it outside of the radical. Simplifying means have no radicals if possible. And so this is how you do that, is you use these rules. You basically need to be able to take that exponent and divide it by whatever your index is. And when you do so, you have done the action of taking the nth root, and you have now removed it from the radical, and that symbol has disappeared. And now it's a lot simpler than it was before. So this is just a very, very tiny, absolutely tiny piece of what you do with nth roots. I mean, we can combine the variables with the numbers. We can have the numbers that we saw not in exponent form. You have to put them in exponent form and then take the root. You have things where you take the root of only part of it and leave things into the symbol. There's so much more that we can do with these nth roots, but this is just the basics here for you to understand what it means to take the nth root, is that it is undoing the exponent. That is the key here. And the key is to know that basically that exponent gets divided by the index. That's really important. And if you have that understanding, that means when you go on to college algebra, you'll have a good foundation for doing all the more complicated things that you can do with radicals. And as far as what you need to know for this class, the goal is to be able to do this with square roots only. And we're really only focusing on numbers. So it's not going to be nearly as in-depth. You're just going to be able to want to be able to take the square root of a number. And if it's not in the form where you can do so, you want to rewrite it in exponent form. And we use our prime factorization for that, which is all the way back from week 1 when we learned how to do that. So just, this class, we're just doing a little tiny bit of this, but it's an important concept. It shows you how whatever we do for square roots applies to any kind of type of root, that a lot of the rules that we learn in algebra apply in many situations, not just one situation. You can see that the rules apply no matter what. So hopefully this has made some sense to you. And if you do have to go on to college algebra, you remember this. And when you start seeing radicals and you start to simplify them, you won't be so confused. So thank you so much for watching, and I hope to see you next time. Bye.